Hey, how's it going, ladies and gentlemen? It's the Flark and Harkin podcast. Just to kind of shed some light on what the podcast is going to be. Sometimes it's going to just kind of be a fun, uh, brief kind of look-see into interesting topics that I find may be of interest to you guys and are definitely of interest to myself. And other times we'll maybe dive into some of the specifics and get a little bit more into the nitty gritty and the math and the hard science behind some of these things. And sometimes we're going to talk about society and culture. Other times it could just be current events in the news. So, anyways, sit back, enjoy the first episode of Flark and Harkin. And today we are going to pop off with dark matter. Maybe get into a little quantum immortality in a little bit, but dark matter's been in the news as of late. If you follow cosmology at all, or the hard sciences a little bit, and dark energy is very interesting because I'm going to kind of talk and assume that the average listener doesn't know very much about it. So please excuse me if some of this is already understood by you. I'm trying to catch everyone up to the same speed, which is going to be like first gear for all this. Anyways, dark matter, very, very, very interesting. We've found out through several ways, which we won't get into, but we have found out that approximately 85% of the mass that we can detect in the universe is comprised of dark matter. So that means about 15% is of visible matter that we actually see, like me, you, the tools you're holding in your hand, the phone you're listening to, or the TV you've got going. That only comprises a very small amount of the matter that we detect in our universe. And kind of an oversimplified way that we know this is that gravity has its effects on particular things, and we know that if a certain amount of gravity is detected, we can deduce the mass of that object depending on the strength of the gravity. So the way we're able to detect that there is other matter outside of visible matter, i.e. dark matter, that's in this universe, is that the gravitational pull from areas where there's not a lot of physical matter that we can see is very strong. So we have to assume that there's something there that's creating this pull or this gravity. And for the most part, we're calling that dark matter. So it's unseen, but we can detect its presence and generate inferences regarding its properties in this manner. And dark matter is hurling through me and you right now. It's passing through people and things. It has properties that are still a mystery to us. We're getting closer to trying to understand it, but we are not very close as of yet. There is a new candidate as of recently, the HexaQuark, which we'll maybe get into a little bit later. So during the creation of things about 13.8 billion years ago, if we kind of assume a Big Bang type of a series of events happened, then there was a certain time in our universe where there was constant creation and annihilation of matter, with no real net gain or loss. So whatever was created was annihilated, and that process happened again and again until eventually we created all matter, both seen and unseen, that we see today. So there was a net gain of matter at some point, and annihilation did not win out. So that includes everything we see and don't see, so both physical matter and dark matter that persists in today's universe. And gravity obviously had a huge impact on the creation of matter as we know it by creating these sporadic mass pools over long time periods. And these mass... God damn it, fucking phone ringing. How am I supposed to record a motherfucking podcast? My goddamn phone rings. Fuck, I'm sorry. Anyways, that's lame. So the galaxies needed gravity to form from dark matter mass because without the presence of gravity, matter couldn't have generated these high density pools, which would later become more complex and eventually form galaxies as we know them. So gravity played a very important role in the creation of the universe as we know it and the galaxies within it. So dark matter can pass through physical matter. Like I said, it's going through me and you. It also has some other interesting properties. It doesn't emit or absorb light, and it's of an unknown size. We haven't really been able to characterize any of the defining characteristics of dark matter. So it may exist not only as a physical particle, traditional in nature, but rather as a wave with presence over a large field of probability statistics. That's basically a lot of mumbo jumbo that takes note of our current understanding of how subatomic particles work and how these particles don't exist at any given point in space-time as we know it. They exist in a wave of points or a wave of possibilities, and it exists in all the possibilities simultaneously, and until we try and measure that particle, it exists in all those, but when we measure it, it collapses, and that particle collapses to a single place in space, point, time, which is artificial. It's a figment of our us measuring that particle. It doesn't really exist there. It exists in several locale at once. It has an opportunity to exist basically in a plane, and we can assign probability to probability statistics to where it may lie within this given plane at any given point in time. Dark matter is composed of particles, I said, that don't absorb, reflect, or emit light. And we have a possible candidate for dark matter as of lately, and that would be the D-star HexaQuark. The D-star HexaQuark is pretty cool. It's a quark or a subatomic particle, i.e. smaller than electrons and neutrons and protons that we know of. And it's composed of 6 quarks. Six quarks. And the D-star hexaquarks may have been crucial during the formation of our universe. And as the universe cooled, the states of matter as we know it were formed. And D-star hexaquarks may have coalesced together, I guess for lack of a better term, during the cooling of our universe to form what's called the Bose-Einstein condensate. And what that is it's like an exotic fifth state of matter that forms when a cloud of atoms or subatomic particles cools to absolute zero. Absolute zero Kelvin, or I believe it's about 460 degrees Fahrenheit, negative 460 degrees Fahrenheit, which would be 270 degrees Celsius. and they clump into an entity described by a particular wave function, like we just spoke of before. And those clumps of particles then behave like a single particle or atom under these mathematical determinants. Right now, we don't know much about the D-star hexaquark, besides it's comprised of 6 quarks. Hence, HexaQuark. That kind of gives it away. But we're still studying the behavior of the D-star and their underlying physics and properties, and would like to know if this is a legitimate candidate for dark matter. It would be nice if we could kind of shed some light on what dark matter is and how things are going with that. Anyways, that's just a little background on dark matter, the D-star hexaquark, which is kind of an interesting recent discovery. This one, for the first one, I think is long enough, so maybe next time we'll talk about quantum multiverses, quantum immortality, which is super cool, which includes the Copenhagen interpretation, which is kind of interesting. But anyways, that's it. Thanks for listening. Hope you enjoyed, and I will speak to you again sometime in the near future. Cheers, mate.